We have talked about Fourier transform on a general finite abelian group last time. Remember, we said that Fourier transform is a basis change for all the functions of this kind. It is a basis change to the character basis. We assumed G was finite abelian last time. The characters were these special functions which satisfied these properties. Everything was happening in this vector space. The group of characters formed an orthonormal basis. That's why we could define a basis change on the character basis. Not just that, we looked at the group Z2 and calculated the Fourier transform explicitly. It turned out to be our old friend, the Hadamard matrix. This could be expanded to Z2 to the power n, and the Fourier transform will become H del Z. We take it to the next step today. We ask, what is the Fourier transform of Zn? This is a slight generalization of Z2, a bigger group, and this is called the discrete Fourier transform or DFT. This has many applications: number theory, complexity, computer science. But let's focus on how or what is DFT for us. Before that, just a reminder, Zn is a group whose elements are all numbers modulo n. The group operation is addition modulo n. That means if I take n minus 1 and add 1 to it, this is going to be 0. Hopefully I have reminded you of what Zn is. This is numbers modulo n with addition. Let's try to find all characters of this group Z. We can talk about the trivial one. Clearly, that is going to be one character. You have numbers 0, 1, and minus 1, and the trivial character will assign value 1, 1, 1 to each of these group elements. Are there any other characters? We know, yes, there should be n characters. How can we find them? Notice that every element of Zn is a multiple of 1. G can be written as k times 1. Using the homomorphism property, chi of k should be chi of 1 to the power k. That makes things easy. We only need to figure out chi 1 to give the complete character. That makes things super easy for us. And what can be the value of chi 1? We know that n times 1 is 0, the identity. We also know that by the property of characters, chi 0 should be 1. So chi 1, or I should say chi of n1 should be equal to 1. By again homomorphism property, chi 1 to the power n should be equal to 1. This tells us that chi 1 should be the nth root of unity. There are n such roots, and this tells you intuitively, and it turns out to be correct. The important thing is each character of Zn corresponds to 1 nth root of unity. Let me go back to some high school mathematics. We will remember what is the nth root of unity? E to the power 2 pi I divided by n. This is 1 and every other nth root of unity is a power of it. So the jth character will take 1 to the jth root of unity, which I can think of as this. Remember here, I is not a variable, I is square root of minus 1. This tells us that chi j of k should be equal to omega jk, where omega is e to the power, the primitive root of unity as we know it. This gives us the complete description. Here j varies from 0 to n minus 1. These are all the characters of Z. Once we have all the characters, we can talk about Fourier transform of Zn. The Fourier transform of Zn is going to be writing all these characters as columns with a normalization. The normalization is going to be 1 by root n. Then the jth or jkth entry is going to be omega to the jk. Notice that my j and k both will go from 0 to n minus 1. J is telling me which character, k is telling me which group element. This comes from Zn and this will come from Zn hat, which is an isomorphic copy of Z. It is going to have n numbers. This is how I can think of the discrete Fourier transform. Simply put, this matrix is the Fourier transform over Z. It will take n vector with n values. I will apply Fn to it, and the Fourier transform will be a vector with n entries. What do we know about Fn? Fn is actually a very, very nice matrix. We can say two things. First is Fn is unitary. And we don't need many tools to prove it because we have done all the groundwork in the previous place. The reason is columns form an orthonormal basis. And we know that any matrix whose columns form an orthonormal basis should be unitary. Those are equivalent definitions, and this will work from the properties of characters. Not just Fn, but if you look at any Fourier transform, it has to be unitary because the columns will be characters and characters are always orthonormal. Knowing Fn is unitary, we know what is the inverse of Fn. This is going to be Fn star. Notice that omega to the jk, if I want to take the star of it, it is going to be omega to the minus jk. And this will let you define what Fn dagger is or Fn inverse is. Not very different. Noticing all these properties, now we know that this is a basis change operator. It takes any x0 to xn minus 1 to y0 to yn minus 1, and we can write this explicitly. The kth element of the Fourier transform is going to be written like this in terms of x's. It is omega jk xj. It is easier to remember even this explicit transformation where each entry can be written in terms of x's. I am just writing the matrix equation row by row. Now, one other thing which is helpful for Fourier transform is called convolution. The special operation, how do we define it? Suppose I have two vectors A and B. Notice A dagger is the Fourier transform of A. This is the notation we are going to adopt. And similarly, B dagger is going to be the Fourier transform of B. Then convolution operator is supposed to have satisfied this property. It is supposed to be multiplicative in the Fourier domain. That means I have to define the operator in such a way such that if I take the Lth Fourier coefficient, it is the Lth Fourier coefficient of A multiplied by the Lth Fourier coefficient of B. This is the property we want to be satisfied. And the way this can be done is that we define A star B, the Lth coordinate, to be 1 over square root n summation this way. It can be defined for all L between 0 and n minus 1. If we define the convolution operator like this, then it will satisfy this property, and I will leave this as an exercise. Convolution is a very important operator in Fourier transform, and this is the reason I mentioned it. It will be good to remember. Now, what is quantum Fourier transform? We know what discrete Fourier transform is. It takes a vector with n coordinates to a vector with n coordinates with the action that yk is 1 by root n xg. I am viewing it as vector. I can even view this x0 to xn as a state. Assume that this is normalized. In that case, this vector becomes a quantum state. Knowing that Fn is unitary, we know that y0 to yn minus 1 is going to be a quantum state. If I call this x, this y, where x is equal to Fny, then an operator, a circuit which does this, is the quantum Fourier transform. This is one of the first tasks or function which I am defining by defining its action on the complete vector space. Look at any vector in n-dimensional complex space. This is coming from C to the n. Then Fourier transform should give us this output, which will be some y0 to y minus 1. You can obviously calculate the action on the basis. That's not hard. That will be given by this equation. So k is going to be 1 over root n This is how the basis will transform, but we also know the action on each and every element of the vector space C to the n. This is called the quantum Fourier transform. We remember omega is the nth root of unity. Notice that since Fn is a unitary operation, Fn is unitary, that means QFT is a valid quantum operation. We can only apply unitary operations. It's a valid quantum operation. Another very important fact, can QFT imply DFT? I will let you think about it for a bit. Pause the video. You will realize that QFT is not it does not imply DFT, because even if we can do QFT, our output is a state whose individual amplitudes are the values we want. In case of DFT, we need YIs explicitly. In QFT, we get a state whose amplitudes are Y. And if we measure them now, we will not get YIs. That shows that actually QFT does not give you DFT. It's a different problem in hand. QFT is a different problem than DFT, though it has a similar flavor and it is useful in many cases. But still, if someone tells you that, oh, we can do DFT on a quantum computer faster, that's clearly not. It turns out that QFT is a much, much faster algorithm than DFT algorithm, but they are solving a different problem. DFT requires n to the 2 point something. This is the coefficient for matrix multiplication. So this many operations at least. There is a fast Fourier transform which can do Fourier transform much faster. It can use n log n operations. On the other hand, QFT only needs polylog n operation. We are going to describe a circuit for it. But notice a stark difference, but this is not a separation. The reason QFT is not the same problem as DFT. Let me write in red to emphasize this. QFT is not same problem as DFT. This will finish this lecture. In the next lecture, we will see a quantum implication or quantum implementation of Fourier transform. So we will perform QFT using